Hello everybody, and welcome to today's presentation, Scaling StreamSets on Azure Kubernetes Service, brought to you by StreamSets. I would like to introduce you to our presenters. Dash Desai, with experience in big data and data science, he's able to apply 15 plus years of full stack hands-on software engineering skills to help build solutions that solve business problems and surface trends that shape markets in new ways than imagined before. As a technical evangelist, he is passionate about evaluating new ideas, trends, and help articulate how a technology can address given business problems. Our next presenter is Sean Anderson. Sean is a tenured big data and cloud strategy consultant with a strong focus on strategic partnerships and innovative open source ecosystems. He has been a key player in integral shifts in technology, including the rise of cloud computing, open source standardization, big data, and machine learning. Sean quickly became a go-to resource and speaker for data-specific workloads focusing on technologies like machine learning, data science, Apache Hadoop, MongoDB, Redis, Elasticsearch, SQL, and data warehousing.
My name is Sean Anderson. I'm Director of Product Marketing here at StreamSets. And here in just a little bit, I'm going to be joined by my colleague Dash Desai, who's actually going to take us through a live demonstration on how to scale the StreamSets Data Ops platform using the Azure Kubernetes Service. And so what I'd like to do is actually just spend a couple minutes to make sure that the audience is familiar with StreamSets, is familiar with what we do on the Azure public cloud. And then we'll turn it over to Dash to kind of visually take us through all of this stuff that we're talking about today. So it's reported that 41% of enterprise workloads will migrate to the cloud by 2020. And this is a pretty aggressive number, considering that a lot of traditional applications and traditional enterprise environments are so coupled to legacy technologies and on-premise systems that this leap to the cloud, while it offers many benefits, is going to be fairly time-consuming and is going to require a lot of strategy and thought and implementing. And so these types of big shifts don't come with an easy road in terms of development. A lot of times it requires additional changes in terms of people and process to make sure that not only are the technology systems and the platforms changing, but the way that the teams develop for these platforms, the way these teams maintain these platforms, we need to ensure that all of that's kind of in lockstep. So these can be very disruptive shifts for companies. But what we're seeing here is that Forbes is saying that the benefits will far outweigh any of the disruptiveness that happens inside these organizations. And these organizations are looking to the public cloud and in specific to the Microsoft Azure platform to really kind of increase data storage and processing scale to meet SLAs. So as big data proliferates, as data sources proliferate, and we start bringing in IoT sources and web native sources and social sources, this really scales the amount of incoming data coming into our data systems. And one of the enhanced benefits of the cloud is that resources can be spun up, often ephemeral resources, to address that very large peak load of data ingestion. And then once that load is no longer there, or in between any of those ingestion processes, users can then scale back their cloud environments to a more manageable cost. And so what we're seeing is that people can really take a look at the workload that they're trying to execute, especially when it comes to data processing, and they can design the architecture to accommodate performance at the very peak of that processing, but then also retrieve the optimal benefits of running a lean infrastructure. And a lot of companies are really looking to unlock net new business value from new data streams, including things like IoT and advanced analytics and machine learning. When you look at the data sources that tend to populate these new world of predictive analytics, they often don't really have a great home under the covers of a traditional data center inside an enterprise company. Many of the EDW or database infrastructures that were built out to run transactional processing and do kind of standard database reporting and visualization are still occupied by a lot of those run the business things. But all of these kind of newer and exciting projects around machine learning and stream processing generally found it hard to find a home on-premise infrastructure. And so the public cloud was a natural fit to kind of bootstrap some of these new initiatives that companies are looking after. And then, a lot of companies are looking to the public cloud to really reduce the cost while also democratizing data across by elastically scaling during peak hours. This is this whole idea of creating, a data lake or a data analytics environment that can be shared out to multiple different stakeholders. And whether you're a data scientist or a traditional analyst, you can apply the tools that you use directly to the data, and then also use self-service tools for data preparation and data processing that can ensure that the data is in the right format when that analyst or data scientist needs to access it. And as enterprise data warehouse architectures continue to expand, their traditional EDWs and they face this kind of problematic scale of big data, the cost and the analytics requirements and kind of all of the proprietary nature of deploying those systems. So the EDW quickly becomes one of the top workloads that people see and migrate to the cloud first, specifically since it provides unparalleled capabilities to share data and create these kind of analytic silos for working on data in a very kind of containerized and specialized way. But again, as I spoke about before, this move to the cloud doesn't come with specific integration challenges when it comes to modern data and existing enterprise systems. The first one is around data operations. So how do you ensure that you're continuously developing, testing, and deploying data systems that deal with real-time and changing data? And these systems have a tendency to break when underlying data streams and infrastructure changes. So once you set up these architectures where you're moving data freely between managed services and data stores inside public clouds and to and from your on-prem infrastructure, how do you make sure that you're continuously improving these data flow architectures and really engineering them to be resistant from change when you have changes in different platforms, in different cloud services, and then also to accommodate the changes that are happening on-prem at your facilities? Data governance and security remains to be a very pervasive issue. And especially as we go into the cloud, many managed services don't have a lot of built-in capabilities when it comes to security and governance. So as sensitive data streams into your cloud are happening, you need to make sure that sensitive data doesn't end up in the wrong hands. Masking data, encrypting data in transit, ensuring data up in the right buckets is critical, and is sometimes an afterthought even for many security conscious organizations. So in this whole idea of strategically understanding how you're going to run your data operations, you really have to understand how you're going to provide a continuous data governance and security experience along with that data. You want to make sure that you're able to ingest any data. Whether that ingestion is happening via batch or via streaming, whether it's structured data or unstructured data. Today, the lines are pretty blurred on how we develop for those systems and what the data actually looks like. So when you're looking at ingesting or processing, streaming, batch, or changing data from a multitude of sources, and you want that processing to happen real time, you need to find a system that can accommodate all of those modes of processing. And especially when users are being managed to or enforced around data SLAs, then we need to make sure that the ingestion of any data, regardless of the format of processing that's happening, can meet those data SLAs. And then the last one we see is really maximizing on the number of workloads and services that we can utilize using the cloud. And so a lot of times initially this is a guessing game. How do we get to a more optimal infrastructure? How do we architect in a way that accommodates all of our data processing and pipelining activities? So, reducing the amount of time that it takes to build these environments, reducing the amount of time that it takes to build a single data pipeline is really going to ensure success. And, when we have ephemeral architectures, we can't really benefit from the kind of transient nature of these architectures unless we can suss out the value very quickly and then terminate those jobs to kind of a more resting state. So with that, one thing that we saw that was clear in the last slide is that this need for a kind of data operations approach to managing data in motion is key. And data ops, which is a new term that was coined just this last November by Gartner in the most recent hype cycle as an emerging trend. And data ops is the automated and process-oriented methodology used by analytic and data teams to improve the quality and reduce the cycle time of data analytics. So the real idea here is that you have systems that can view data holistically, that can engineer and reuse and automate the movement of data between multiple different enterprise systems, and that can provide that level of management and visibility and data protection that enterprises require. And more importantly, they can provide that same experience on-premise as well as on the public cloud, really with a seamless developer experience and a seamless experience in the management of those data pipelines. So we believe that a data ops platform, and more specifically the StreamSets platform, provides automatic testing of data pipelines to ensure that the right data processing stages are happening. We detect for a common phenomenon called data drift, in which data manifests changes in semantics as well as structure as it's moved in between systems. You can manage that all with an interactive UI. So if you don't know how to hand code specific pipelines, then we give you a very logical and linear environment in order to do that. And then once you've created those pipelines, you can store them in a repository to be used by yourself or other team members at another time. When talking about that continuous governance aspect, we allow for the masking of sensitive data to happen directly into pipelines. So you can build that logic directly into the pipeline instead of having to enforce it more holistically. We also take the policy and access controls that are enforced by your other systems and enforce those in stream as well. We can provide encryption for data streams, so data can't be read across transit. And then we really accommodate the scale of big data and the variety of big data. So you can incorporate with many big data systems, and we can scale to meet the same volume of data that the big data systems are incorporating. And then what we're going to show today is a really handy way to actually scale out that ingestion capability as data volumes start to grow. And in watching this, we want to remind you that the StreamSets platform can be deployed anywhere on any cloud manufacturer, although today we're going to be specifically focusing on the Microsoft platform. It can be deployed on-prem, and through our Data Collector Edge product, you can also do processing and bidirectional communication directly through that Edge protocol, which is very lightweight and runs on less than 5 megabits of processing space. So here's a little look of a common scenario that we see, and this is really about migrating to the initial migration to these cloud sources. So you'll see on the furthest left-hand side, you have on-prem database and data warehouse sources. Maybe they're Oracle, maybe they're Greenplum, Teradata, MySQL. We host a variety of connectors for popular database systems that can kind of be dragged directly into our UI as kind of set sources and destinations. We can pull in data from different enterprise cloud services like Salesforce and Adobe Analytics. We can also leverage data that exists natively in the cloud from day one, and then we can incorporate those edge devices. And then with the StreamSets platform, we can design the ingestion and data processing of that data coming in. With StreamSets Control Hub, we can monitor the movement of all data across those systems. And with Dataflow Performance Manager, we can actually drill into specific hotspots and areas where we think that data movement is either failing or is not performing to expectations. And then with that, we get it into the Microsoft ecosystem where data can be stored, data can be analyzed either by data science teams using a service like Databricks, or through popular managed services on the Azure platform like Azure SQL Data Warehouse or some of the other services. And then from there, we can connect natively, any specific BI tool, any visualization tool, to then start running advanced analytics directly on those data stores and managed services. So this is really just an example, but I wanted to hand it over to Dash. Dash is going to talk specifically about how we handle the scaling on the front end of these interactions and how users can think about developing and leveraging the Azure Kubernetes Service to actually help achieve that scale with minimal complexity in the design. And so Dash, I'd like to turn it over to you now. And audience, I hope you find the demonstration enjoyable.
Great, thanks a lot, Sean. And thanks everyone for joining us today. We really appreciate you guys taking the time. My name is Dash Desai, and I'm Technical Evangelist here at StreamSets. And as Sean mentioned, today I'm going to show you how you can deploy and scale StreamSets on Azure Kubernetes Service. So I'm going to go ahead and start sharing my screen. Let's see, okay. So hopefully everyone can see my screen. Before we get started though, let me describe the environment I have set up for us today. Okay, so I have a Kubernetes cluster running on Azure. And as you can see, here's the dashboard for it. It's got 3 nodes, and I've basically used the default configuration for the demo today. StreamSets Control Hub is running in a hosted environment, as you can see right here on the screen. And the type of data we'll be working with today is web server logs, which includes HTTP requests for page views, products, and so on. Here's what the raw data looks like. It's got IP addresses in there. It's got HTTP codes, HTTP methods, get, post, and so on. It also has the URL that was requested by the client. The primary data source for today's demo is Amazon S3, but in practice, it could be any other cloud-based data source, a file system including Hadoop, or a remote SFTP server, for example. Here's the bucket, and here's the weblogs file, which is about 37.8 megabytes in size, and it has about 180,000 records. And the final destination where the logs will be stored is Snowflake. But again, depending on your use case, it could be any other data store, including Azure SQL Data Warehouse and so on. Let's quickly look at the Snowflake Dashboard. So today we'll be working with a database called dash_db and schema called retail. As you can see, there's no tables, and we'll see how all of these gets populated and created automatically as we go through the demo. So at a higher level, the example use case that I'm going to demo today is to ingest web server logs, store them in a format such that they can be queried and analyzed. And before we look at all the details and how everything comes together, I'm going to take a minute to describe how things work top to bottom, starting with the auto-scaling components down to execution engines and their data flow pipelines. I'm going to switch over back to StreamSets Control Hub. This is the main dashboard. And we're going to start with provisioning agents. To automatically provision data collectors, a containerized application, also known as a provisioning agent, is configured to run in a container orchestration framework, which in our case is Kubernetes, a cluster running on Azure Kubernetes Service. These agents communicate with StreamSets to automatically deploy, start, scale, and stop data collector containers. And provisioning an agent is especially useful when you require a large number of data collectors to run jobs. Provisioning data collectors also means that you're taking advantage of all the benefits that Docker and Kubernetes have to offer, including easily scaling and updating containers to a new image with a different version of data collector or with a different set of configurations. So here's one that I've created for today's demo. This agent was actually created and deployed using Kubernetes, using a script similar to this. So the script uses Azure's Kubernetes and StreamSets command line interfaces to create, deploy, and register the agent. But it's important to note that you can also deploy these agents using Helm. Next up is deployments. Here are the two that I've created for today's demo. Deployments are logical groupings of data collector containers that get deployed by provisioning agents like we just saw. And all data collector containers in a deployment are identical and highly available. The logical grouping of these data collectors is based on the labels that are user defined. And we can also scale up and down data collectors by increasing or decreasing this number. And I'll show you how in a minute. And once the deployment is activated, for example, let's go ahead and activate this. The instances of the number of data collectors specified will be launched on Kubernetes cluster. Let's look at jobs. Jobs let us specify which pipelines to run on which set of data collectors, again, based on labels. So in this case, it's AKS dash to Kafka. They also provide a failover ability to minimize downtime due to unexpected pipeline failures. And you can also define parameters that get passed down to pipelines. So you can run instances of the same pipeline with different parameter values passed in via jobs. And lastly, we have the actual pipelines that do the work. This is where you describe and design the flow of data from origin to destinations and can optionally include transformations on the data along the way. Let's look at the very first pipeline to begin with. It's designed to read logs from S3 and write them to a Kafka producer. Note that S3 origin in StreamSets has a built-in log parser. So for example, attributes like HTTP URL, response codes, client IPs, they will be automatically parsed into record fields. Using field type converter, we're converting attributes like timestamp, bytes, HTTP versions to their respective data types, because they come in as strings from the CSV file that we have. Expression Evaluator enables us to decode request URL and gives us the ability to also parse out product names using regular expressions that's applied to the URL. Geolocation Processor lets us enrich our data set by capturing location based on the client IP that's present in logs. So we're capturing city, latitude, longitude, and country. And finally, we've added a pipeline finisher executor, so the pipeline will automatically stop once all the logs are written to Kafka. The Kafka, I've created a single node simple cluster that's running on EC2, and the broker URI as well as the topic is provided as a parameter via jobs. So before we look at the second pipeline, which will take all the logs, transform logs from Kafka and put into Snowflake, let's get the data flowing from S3 to Kafka first. So first off, I'm going to make sure the Kafka and Zookeeper are up and running. So that looks good. I'm going to use an open source tool just to show you the broker that I have set up and the topic with 6 partitions. And I'm going to refresh to make sure there are no messages as of right now. So it's 0. Now let's go back to the control hub. And let's look at the deployments. So this deployment has been activated, which means it should have at least one data collector deployed on Kubernetes. This will show up under data collectors with label AKS to Kafka. Again, this was based on what was specified in the deployment. You can also use Kubernetes the command line interface to see how many pods have been deployed. So the command is to get pods, and it should show us 2, 1 for the agent itself, and here's the data collector pod that was just deployed. Okay, so back to jobs. And our first job is to get data from S3 to Kafka. So I'm going to go ahead and activate the job. Okay, so what we can actually do is look at what's actually running on the data collector that was deployed. So for that, I'm going to switch over back to the terminal window. Actually, first, let's refresh our Kafka tool to see that the messages are being written to Kafka producer. We can look at the pipeline, a cool port forwarding trick that you can use that's provided by Kubernetes command line interface to actually look at the data collector UI. So now if I go ahead and do a new tab, localhost, so here's the data collector. It looks like the pipeline's already finished because of the pipeline executor that we have within the pipeline. So that was pretty fast. Now if we go back to Kafka tool, refresh, and we should see about 180,000 messages that have been written to Kafka. Okay, great. So now we have transformed logs ready to be consumed from Kafka. Let's look at the second pipeline. I'm going to go ahead and close this. StreamSets Control Hub. Here, all we're doing is reading logs from Kafka, converting timestamp from epoch to timestamp, and then storing them into Snowflake. Here's the warehouse that we saw earlier, the database, and then the schema. A couple of things to note here. Snowflake destination will automatically create this table, web logs, if it doesn't exist. So just for sanity's sake, let's make sure the web logs table does not exist. So that's our setup. Now, let's start ingesting logs from Kafka to Snowflake. So again, I have a job set up for this to run this pipeline. So I'm going to go ahead and, first of all, we have to activate the deployment. This will take just a few seconds. Again, if I were to run this command, we should see a new data collector pod being deployed. It's running. If we just takes a couple of seconds for heartbeats to go back and forth. We should see it pretty. Okay, so here we have our data collector that's been deployed. We can also see it here if we filter by the label to Snowflake Kafka. Now we're ready to start our second job, which is taking the logs from Kafka to Snowflake. Go ahead and start the job. Let's quickly look at the data collector running. I'm going to go ahead and close this. That was for the first pipeline. And this data collector should show us the second pipeline that's ingesting data from Kafka to Snowflake. Go back, localhost. Okay, so as you can see, things are moving along. We have here you can see the metrics for the pipeline. Clicking on these, you can see individual stage metrics. So it looks like things are moving along pretty fine. Now let's see how we can scale data collectors without stopping our jobs or pipelines. So for that, I'm going to go back to our deployments. This is the one that we'd like to scale up data collectors. I'm going to go ahead and increase to say 3. Click on scale, and let's look at the terminal. As you can see, we have 2 new pods being deployed for this deployment to Snowflake. If we go back, we should see data collectors being registered. There you can see 2 additional data collectors. So if we filter based on the label, here are the 3. And let's see if we can port forward to one of the newer ones. Yeah, okay. You just need the command for it. Okay. And then date 889, and then 18630. Typo. Okay. So this is our first data collector, and then we're going to look at the second one that was brought up, and then we auto-scaled. So here's the second data collector. Okay, and then similarly, we can look at the third one, right? If we go back to our interface, we should see that the pipeline's running on all three of them. And you can also see that within the jobs interface. So if this is the job that's active, and then if you click on data collectors, you will see the three data collectors running that the jobs running the pipelines on. So there are a lot of things that you can do to improve performance, such as number of threads, Kafka producers, consumers, partitions, cluster nodes, and so on. But that's beyond the scope of this demo. So everything you've seen is out of the box experience with default configurations. So now I'm going to go ahead and show that the data has been stored in our Snowflake. So here's the table that was automatically created by StreamSets Snowflake destination. And as you can see, go ahead and run this query. We have about 110, and the number should be going up. And we can start actually running the queries against our log. So for example, this query will show us the count based on how many requests were successful versus how many failed and so forth. We can run queries that are location based. For example, this one shows us HTTP requests by cities. We can also, because we were able to extract the product name from URLs, we can run a query such as, top 10 most viewed products. Right, and then if we look at the count just to see where we're at. So we're approaching the total number. One thing I want to highlight, so we had about 180,000 messages. If we go back to our Snowflake destination, there is I've set a precondition where I'm ignoring records where latitude is null. So for whatever reason, we could not get location information based on client IP. Those are the records that I'm discarding before storing into Snowflake. So that's why you will see a little discrepancy between 180 versus the total number of records we will have in Snowflake. Okay, cool. So one thing I want to note also is that data collector itself is open source and can be downloaded by visiting this page. And it can be installed independently and then optionally registered with Control Hub to take advantage of managing hundreds of pipelines, scaling on Azure or Google Cloud, data protection, etc. So just want to quickly show you, I have a data collector instance running locally on my Mac. And here's what it looks like. So again, very similar to what we just saw from within Control Hub. So that's the demo part. But before I hand it back to Sean, I'd like to highlight a couple of more things. First, topologies. So topologies make it easy to visualize end-to-end data flows across multiple pipelines. And they also enable you to measure and monitor data flows across jobs, as well as set data SLAs. So here's one that I've created for this demo. Okay. Actually, since I deleted the pipelines, it is invalid because of my previous runs, but basically you get the idea. So let's just create, actually, no, in the interest of time, we won't create a new one, but the idea is if you can add, let's see. Once you design this, you can, in this designer, you can add multiple jobs and connect them together. So here, what we're saying is we're ingesting logs from S3, we're storing them to Kafka using these set of pipelines that are probably not valid because of my test run. And then once the data goes into Kafka, we're storing them into Snowflake. But the cool thing is from here, instead of individually running these deployments and jobs independently, you can start all jobs and you can start, or stop all jobs with a click of a button. And you can see that overview and you can look at metrics in the unified interface as well as set data SLAs. So the second thing I wanted to highlight is everything that you've seen so far can be automated using the scheduler and the REST APIs. And there's some examples and a lot of documentation around it on the website. So I think that's it for the demo piece. Thanks again for your time today, and I hope this was educational. And back over to you, Sean.
Okay, Dash, sorry for the silence there, guys. Apparently I can't do two things at once here on the system. So Dash, thank you for that demonstration. You really made it seem very simple to deploy those containerized instances. I do want to invite everybody on here to submit your questions. If you have any questions about the material we presented today, about the demo, about the environment that the demo was run in, or even Control Hub, which Dash showed there at the end, please submit those questions to us today. I do see one quick question, and Dash, I know you showed the ability to provision those data collector instances, but is there scenarios where you would want to horizontally scale those instances, and how would you think about designing that?
Absolutely. So good question. There's a concept of horizontal pod autoscaler, and when we create these deployments, you can actually set an attribute in the YAML file, the configuration of the deployment, where you can say you can give a percentage for CPU usage, and the system or control StreamSets platform will auto scale based on the percentage that you specify while creating the deployment. So it's as simple as just adding that attribute in deployment YAML file.
Got it. So that seems to be pretty simple as well.
Correct. And there's detailed documentation on our website on how to do it and so forth.
Okay, fantastic. So to learn more, people should check out our website.
Correct.
Gotcha. So I know in this example, Dash, you're loading data from S3. For people that are specific to the Microsoft ecosystem, do you have similar recommendations and the architecture around data storage?
Absolutely. So like I mentioned during the demo, the data source can be anywhere, including Azure, blob store, or a file system, a Hadoop-based system. So it doesn't really matter as far as this goes. The reason why I chose S3 was just to show how the StreamSets platform can work across different clouds.
Got it. Fantastic. That last screen that you showed there with Control Hub, you talked a little bit about automation. I'm curious, this person's curious, specific to cloud workloads, can you think of some instances where that you would use that automation to either get better cost savings or better performance?
Definitely. So the automation piece was kind of focused around not having to start and stop manually. That was to show what different things you can do. So with using our scheduler, you can schedule these jobs to be either started at a particular time, and also you can use the REST APIs to actually create topologies or jobs, create deployments and so forth, externally using scripts. So does that make sense? And as far as I think scaling goes, it kind of depends on a lot depends on the use cases, and definitely you can take advantage of, for example, HPA based on CPU usage and so forth.
Great. Well, I think we should cover just a couple items about the platform real quick before we let everybody go. If you have any additional questions, we've got a couple more minutes, so feel free to throw those in there. And then if we don't have any more, we'll close it out. But if we do, we'll try to get those if we have time. So you have a couple options when deciding how you want to deploy or kind of try out the StreamSets DataOps platform. Generally we want you to understand kind of what does your workload look like? Are you bulk migrating something up there? Do you need to have incremental uploads from there? What does the actual data loading look like? Are you trying to rehost an existing system in the public cloud? Or are you trying to build a net new system for new types of analytics and new types of data integration? And then you can test us out. We are listed on the Azure Marketplace, which you'll see on the right-hand side here. Specifically StreamSets Data Collector. So Dash pointed out that it is an open source download, so you can feel free to go to our website and download it from there. But if you live natively on the Azure Marketplace and would like to just deploy it through that mechanism, we are available on there. So if you have any questions about how that's deployed, you can reach out to our team. And then if you would like support on your environment and you would like mechanisms like Control Hub and the performance monitoring, the data protection, please reach out to us here at StreamSets and we can take a look at your use case and try to figure out the best solution for you. And then, on the backside of this conversation, we don't want to end the talk right here. Feel free to reach out to both Dash and myself. Our Twitters are located here. I am on the net, Sean Anderson BD. This content today was actually based off of a blog that Dash authored. That blog is available on our website. So if you go to streamsets.com, you can navigate directly to our resources section, to our blog, and you should see Dash's full write-up on the front page there. And then we have a very vibrant and active community. And so you can interface with us via Google Groups or via Slack in our community and tell us what you're doing with public cloud services and data streaming as well. So we invite you to join that community and see what you can build with these types of technologies, and hopefully you can accelerate your analytics or your product design. So with that, I'm going to go ahead and close out our conversation today. I want to thank DZone for hosting us on this great webinar, and I want to thank Dash for putting together such a great demonstration and doing it live here today. I know that's always kind of a tricky proposition. So with that, thank you all for your questions. Thank you for attending today, and please let us know if you have any questions.
Great. I'd also like to pass some thank yous along. Thank you for Dash and Sean for hosting this great presentation today. I'd also like to thank today's sponsor, StreamSets, for providing the audience with a great webinar presentation. And lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Have a great day, and we'll see you next time.